So odds are you're on the internet these days. But what does that actually mean? And indeed, this internet that we use very often these days for messaging, for email, for browsing the web and other services still, there's a whole infrastructure that underlies it that is increasingly powering new ideas, new startups, new companies, new businesses, as well as new forms of communication among humans. And yet, like most every topic we've explored, you'll realize that while it's very complex perhaps up here, or certainly seems complex up here, if we begin with some of the fundamentals and then layer and layer and layer on top of those, do we pretty quickly get back to today's technology, but with a much better understanding of what's going on from the ground up. So here is a bit of alphabet soup. Odds are you might have seen one or more of these acronyms to date: IP, DHCP, DNS, TCP, UDP, ICMP, and so many more. These are all examples of something called protocols, where protocols are kind of like languages that computers speak with one another. They're not programming languages, so they're not used by humans to make computers do things or follow instructions per se. A protocol is really a set of conventions that two computers or two computer programs might use when intercommunicating. And so what's an example of a protocol in the real world? Well, we humans have some silly protocols, one of which here is culturally when you meet someone to extend your hand, and then he or she presumably extends their hand, and you do this for who knows what reason, and now you've sort of completed that social transaction. But it's a protocol in the sense that when I extend my hand, most any polite other person knows that they're probably supposed to extend their hand as well, embrace for a moment, and then complete. And the protocol says, too, you probably shouldn't do this for terribly long. And so there's these rules of thumb, or actual rules that you follow when implementing protocols. And so computers, great as they are at following rules, very often use protocols when they intercommunicate in order to get data from one place to another. So let's tell exactly that story. If you're on the internet, indeed right now on the internet, what does that actually mean, and how can it help us solve problems ultimately, having access to this inter-networked infrastructure? Well, let's consider what happens when I first visit my favorite web page, for instance. If I go ahead and visit something like Facebook.com, I go ahead and log in, and I'm immediately presented with my news feed. Or maybe your favorite website is Gmail, or your favorite website is Bing, or maybe your favorite website is any number of other places you might go on the web, all of which take in as input a request from you and produce ultimately output, the screen that you ultimately see. But how does that data get from one location to another? Let's begin to draw a picture, perhaps. And this picture might be representative of your own home network, or maybe your campus network, or maybe your office network. But generally speaking, you are on the internet, maybe with your phone or your laptop or your desktop device, and we'll just depict that as this sort of abstract laptop here. So that laptop somehow wants to communicate with a web server elsewhere, Facebook, Google, Bing, whatever, and we're just going to present that as way over here in the picture in a really big corporate office building, perhaps. And inside of that building are the servers that compose that particular website. But how do I get data from that server, which if it's Google or somewhere else might be all the way in California or halfway across the world, and back to my laptop? Well, somehow I have to be able to send messages to it and receive messages from it. And of course, in between me and this resulting website is what we'll generally call the internet. It's kind of conveniently drawn as a cloud here, which is another semi-technical term that's come into vogue in recent years. And the cloud really just refers to internet services these days. It's not a technical term unto itself. It's just a sexier term than saying, my business is on the internet. Oversimplification, and we'll come back to that before long, but you can assume near that the internet is somehow this delivery mechanism. It somehow gets data from point A to point B and back. But how does that work? If my data is coming in as input and it's reaching eventually its destination, and then a response is coming back in this direction, what's actually going on underneath the hood there? Especially since, in the story at hand, all I've typed is something like Facebook.com or Gmail.com or the like. Well, it turns out that your computer these days, when you first turn it on and you connect to like the Wi-Fi or in a room, or you connect with an Ethernet cable to the wired network, your computer receives some information automatically. Your computer speaks a protocol called DHCP typically, Dynamic Host Configuration Protocol. But in most of these cases, the acronym isn't really what's important, certainly. It's what the protocol itself does. And in this case, this Dynamic Host Configuration Protocol dynamically configures hosts via a protocol, if you will. So what does this mean? Essentially, DHCP says this. When you turn on your computer or you take out your phone for the first time and you're connected on Wi-Fi or to a wired network, it says, hello, world. I am alive. I would like to be given an address so that I can communicate with other computers on the internet. It's not quite that verbose, perhaps, but it is a question. Hey, computers around me, please give me an address. And what it gives you is what's called an IP address, Internet Protocol. So just as in the real world, where physical buildings have historically been uniquely addressed with postal addresses, like Harvard's computer science building is at 33 Oxford Street, Cambridge, Massachusetts, USA. 02138 is the more precise zip code as well. That uniquely identifies that building in the world. So does my computer need an address. And it's not going to be some free-form address like that in words. It's actually going to be a numeric address. Specifically, I'm going to get an IP address of the form number, dot number, dot number, dot number. So 4 numbers separated by dots. Each of those 4 numbers happens to be a byte long, or 8 bits. So each of these numbers, therefore, is between 0 and 255. And so this means, long story short, that the total address is 32 bits, 8 plus 8 plus 8 plus 8. And that means there's 4 billion possible addresses in the world. And that's great, because people got a lot of computers and a lot of laptops and a lot of desktops and servers these days, but it turns out we're actually running out because we have so many such devices. So there's a newer version of IP that's increasingly being used called IP version 6. We're talking here about IP version 4 since it's so omnipresent. And IP version 6, just so you know, uses 128 bits for its addresses, way more than 32. So we'll be good to go for some time. But DHCP gives me this address, an IP address of the form something dot something dot something dot something. And the purpose of this address is to help my data get from point A to point B. And indeed, anytime my computer sends a request out on the internet, like Facebook, please show me my newsfeed, or Gmail, please show me my inbox, my computer has to use that IP address. So much like if sending a letter in the real world, you might have an otherwise blank envelope, and you might want to send a message to someone else in the world. You might write their physical address, but in the computer world, we might write something like 1.2.3.4 in the to field, assuming that this is the IP address to which we want to send this data. Meanwhile, my from address might be 5.6.7.8, so I'll write it in the top left-hand corner by convention, whereby that indicates to the whole internet, this is where this request came from. Now, I know my origin address, the source address here at top left, because DHCP told me. How do I know 1, 2, 3, 4? How do I know the IP address of Facebook.com or Gmail.com? Right? We don't live in the world of 800 numbers anymore, where you dial 1-800 something 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 something, and you have to advertise your phone number per se. We don't necessarily live only in the world of 1-800-collect anymore, where we had these mnemonics where you had letters mapping to numbers just to help remember it. We went full in on this idea of mnemonics, such that now we have Facebook.com and Gmail.com, and no numbers whatsoever for us humans to remember. So thankfully, turns out there's another system in this world, another acronym, if you will, a new one now, called DNS, Domain Name System. So there are also in the world not just DHCP servers that hand people IP addresses from their local network. There's also DNS servers whose purpose in life is to convert domain names to IP addresses and vice versa, and a few other features as well. Now, what does that mean? That means that when my Mac or my PC sees little old me, the human, typing Facebook.com or Gmail.com, my laptop contacts a nearby DNS server and says, hey, my human has asked me for Facebook.com. What is its IP address? And a DNS server's purpose in life is to answer that question and say, oh, Facebook.com, it's 1.2.3.4. Use that address instead. Now, thankfully, my computer can now write that number on its virtual envelope, so to speak, and then pass that envelope out to the internet. And because of these numeric addresses, it will be properly, hopefully, routed across the internet to its destination. Because it turns out inside of the internet here, interconnecting everything in between point A and B are things called routers, or gateways. And I could draw this picture in any number of ways, but the point is that it's just so darn interconnected. And indeed, there might be even more pathways still, or maybe even fewer pathways. Indeed, on the internet, there's often multiple ways for data to get from one point to another, some shorter, some longer, but there's this resilience, this redundancy. And this was a feature back in the day, especially insofar as the internet had militaristic origins. It was meant to be redundant so as to withstand failures of one or more of these nodes, these dots in the picture. Now, each of these dots is just a server, really, a special server called a router or gateway, whose purpose in life is to do exactly that, to route data. Upon receiving a virtual envelope like that one, it looks at the to address, realizes, ooh, this is destined for 1.2.3.4. I know that that address is over this way. Meanwhile, if it gets another envelope from someone else, it might say, ooh, this is some other address. It's going to go this way. And so routers have multiple cables, or they have multiple virtual network connections elsewhere, or wireless connections. Any number of possible connections might they have to other routers. And so it can route it to its next hop, so to speak. And generally on the internet, within 30 hops, within 30 transmissions from router to router, will your data get from one point to another. And it might not follow the same path each time, but it will traverse this so-called internet. And so that's kind of what the internet is. It's this collection of routers, and it's this collection of networks, a network of networks that is incredibly interconnected in different ways. So DHCP gives me an IP address, so I have a unique IP address. DHCP, turns out, also tells me what the IP address is of my local DNS server, so I know whom to ask to convert domain names to IP addresses. But once I have that, I can now use a protocol called TCP to send my data reliably, typically from one point to another. So whereas IP is responsible for a few things, one of its most important functions is this notion of addressing and standardizing how things are addressed. But TCP, one of its most salient features is to guarantee, with high probability, delivery. And what I mean by that is that bad stuff can happen in the middle of the internet. These routers can get really busy. They can get really congested and overloaded. And so routers might virtually drop packets. They might receive so many packets at once, they just can't, like a human, deal with it all at one time because they have a finite amount of memory or RAM or disk space, and so they drop them, so to speak. They just delete them, and they expect the senders to resend them. TCP is a protocol, another agreement between computers, that if the receiving computer realizes, I got some of your packets but not all of them, TCP mandates, much like our human handshake, that something next should happen. TCP says my laptop should retransmit that virtual envelope. But TCP allows us to do something more than guarantee, with high probability, delivery of data. It also allows us to multiplex among services. Or put more simply, it allows a server to receive different types of data for different types of services. For instance, web services on the server, email services, chat services, and the like. And so it turns out that on this virtual envelope that gets sent from a computer to a server, it's actually not sufficient for there to be the return address and the IP address of the destination. I also need to specify what type of information is inside this envelope, or equivalently, what kind of service I'm trying to contact. And I could do this by specifying in words what's inside this envelope. Maybe it's something like HTTP, the prefix that you're familiar with from the web. Maybe it's an email. Maybe it's a chat message or the like. But if it is, in fact, something like HTTP, turns out the convention is not to use words, but to use numbers. And so, in fact, I need to put one other piece of information on this envelope, which is a so-called port number, a TCP port number, which is numerically printed after a colon on a virtual envelope like this. And in this case, I wrote 80, because 80 happens to be, by human convention, the number we humans agreed on some years ago identifies web services on servers. But this means that if the server I'm sending this to, 1.2.3.4, actually has other services on it, like a chat server and an email server and the like, this won't get confused with an email that I or someone else am sending to the server, or a chat message. The server will know upon receipt of this, oh, this is a request for a web page. Let me send this virtual envelope to the web server. But HTTP isn't the only such protocol. There is something called UDP, which is common in some circles as well. UDP works a little differently insofar as its feature is to not guarantee delivery. If some data gets lost, packets get dropped, so to speak, for whatever reasons, malfunction, technical difficulties, routers are overloaded, UDP says, our protocol shall be not to retransmit that data. And that's a strange thing, because it sounds worse, and yet this protocol has been around for quite some time, still used, quite appropriate in some contexts. But what context would you actually want to just forge ahead, irrespective of getting complete information? Well, go-to here is something like video conferencing or audio conferencing or live TV on the internet.